Beneath the golden, sun-drenched hills and sprawling valleys of California, a silent and invisible drama is unfolding. Every day, as millions go about their lives, a hidden tension is building deep below the surface, a tension that has been quietly accumulating for generations. This pressure, imperceptible to those above, is the result of forces that have shaped the very face of the Earth for eons. For more than a century, scientists have watched and waited, knowing that California is living on borrowed time. Far beneath our feet, the Earth's crust is not a solid, unyielding shell, but a patchwork of massive plates, constantly grinding, shifting and colliding. The San Andreas Fault, a colossal scar stretching hundreds of miles, marks the boundary where two of these titanic plates meet. This fault is the source of a threat that looms over California, a threat known simply and ominously as the Big One. The question is not whether this great earthquake will strike, but when. The clock is ticking and the countdown is written in the slow, relentless movement of the Earth itself. Scientists warn that when the Big One arrives, it could unleash a quake of magnitude 7, 8, or even greater, an event powerful enough to reshape cities and lives in a matter of moments. The potential devastation is staggering. Billions of dollars in damage, entire neighborhoods reduced to rubble, and the possibility of thousands of lives lost in the chaos. This danger is not an abstract concept. It's woven into the very geography of California. The San Andreas Fault is a living, breathing boundary, a reminder of the planet's restless energy. Nearly 30 million people call this state home, and more than two-thirds of them live and work within reach of this immense fault system. Their daily routines unfold atop a sleeping giant. California's great cities, Los Angeles, San Francisco, San Diego, are vibrant centers of culture, innovation and diversity. Yet they are also perched on ground that could, at any moment, become violently unstable. Los Angeles, a sprawling metropolis of over 10 million, and the dynamic Bay Area with its iconic bridges and tech hubs are both perilously close to the heart of this geological threat. The infrastructure that sustains this vast population, freeways that snake across the landscape, aqueducts that deliver precious water, power lines that light up the night, are all vulnerable to the forces gathering below. The Big One is not just a single earthquake. It's the culmination of decades, even centuries, of strain, released in a sudden, violent burst that can trigger a cascade of destruction. In a matter of minutes, the strain of lifetimes is unleashed. The ground, so familiar and solid, becomes a force of chaos. The earth will not simply tremble, it will crack open, tearing through roads, neighborhoods and memories. Streets will buckle, homes will lurch, and the familiar will become unrecognizable in the blink of an eye. Buildings that have stood for generations, schools, homes, landmarks, could be reduced to ruins, their histories buried beneath the rubble. The very landscape itself may be forever changed, as valleys shift and hills rise, reshaping the map of California in an instant. For millions, this is a reality that lingers at the edge of awareness. Life goes on. Children play, families gather, cities pulse with energy, yet the threat remains, silent and patient. Every step taken on California soil is a step on a geological knife edge, where the ground beneath could shift without warning, rewriting lives in an instant. This is not a tale of doom, but a story grounded in science and history. Decades of research, observation and hard-won knowledge have revealed the patterns and risks that define life in California. Our planet is alive, its surface in constant motion. The continents drift, collide and reshape themselves in a slow, relentless dance that has been ongoing for billions of years. California sits at the crossroads of this planetary ballet, where the Pacific and North American plates grind past each other, storing energy that will one day be released. The San Andreas Fault is more than a line on a map. It's a living boundary, a place where the forces of creation and destruction meet. The forces at work are as relentless as the tides, as unstoppable as the rivers that carve through California's canyons. But knowledge is power. Understanding the threat is the first step toward preparing for it, toward building a future where Californians can face the big one with resilience and hope. We must look at the immense power of our planet, not with fear, but with respect, curiosity, and a determination to adapt and thrive alongside its incredible forces. The story of the big one is, ultimately, the story of humanity's enduring relationship with the restless, magnificent planet we call home, a story of risk, resilience, and the unbreakable spirit of California. The San Andreas Fault is a magnificent and at the same time deeply unsettling feature of our planet. It is a testament to the restless, ever-changing nature of the earth beneath us, a reminder that the ground we walk on is not as solid as it seems. This fault is a gigantic scar, carved into the earth's crust over millions of years. It's a visible record of the titanic forces that have shaped California's landscape, splitting mountains, redirecting rivers, and creating valleys that define the region. The San Andreas is not just a line on a map. It is a complex, dynamic zone of shattered rock, stretching for over 1,200 kilometers, nearly 750 miles across California. Over eons it has shaped the very geography of the state. The fault begins near the Salton Sea in the arid south, carves a path just north of Los Angeles, and continues its journey up the coast, past the iconic city of San Francisco. Its presence has influenced where cities have grown, how roads and railways are built, and even the course of rivers. This immense fracture marks the boundary between two of Earth's great tectonic plates, the Pacific Plate to the west and the North American Plate to the east. The grinding, sliding and jostling of these plates is the engine behind California's dramatic geology. The movement along this fault is constant, yet often imperceptible. Over time, the relentless grinding has pulverized rock into a fine, powdery substance known as fault gouge, a silent witness to the fault's ceaseless activity. The Pacific Plate is slowly but inexorably grinding its way northwards, carrying with it a slice of California that includes Los Angeles and San Diego. This movement has shaped the state's topography and even influenced the location of its earliest settlements. The plates move at a rate of about 50 millimeters per year, roughly the same speed at which a human thumbnail grows. Over centuries, this slow but steady pace adds up, shifting entire landscapes and bringing distant cities ever closer together. This relentless journey means that over geological time, Los Angeles is inching ever closer to San Francisco. The fault's movement has played a role in shaping the growth and character of California's cities, influencing everything from architecture to emergency planning. But the movement is not smooth. The fault's path is marked by jagged rocks, abrupt cliffs, and sudden changes in elevation, evidence of the violent forces at work below. In many places, the two plates are locked together by friction, unable to slide past one another. This creates long periods of eerie stillness, punctuated by sudden, catastrophic movement. As the plates continue to push, strain builds up in the rock, like energy being stored in a coiled spring. The longer the plates remain locked, the more energy is stored, waiting to be unleashed. This stored energy is the source of the earthquake threat. Scientists use sophisticated instruments to monitor the fault, searching for signs that the spring is about to snap. When the strain becomes too great for the rocks to bear, they will snap. The fault ruptures, and the pent-up energy is released in a burst of seismic waves, shaking the ground with incredible violence. These earthquakes have shaped California's history, toppling buildings, altering landscapes, and leaving lasting scars on communities. The San Andreas is not a single clean break. It is a tangled web of fractures, a whole system of interconnected faults that crisscross the state. This network of cracks means that the danger is not confined to a single line, but is distributed across a wide and heavily populated region. Earthquakes can strike far from the main fault, catching communities off guard. In the Bay Area, for instance, the dangerous Hayward and Californian faults run parallel to the main San Andreas, each capable of producing its own devastating earthquake. The 1868 Hayward Quake, for example, was a stark reminder of the region's vulnerability. This complex network of faults means that millions of people live, work and play atop a restless landscape. The threat of earthquakes shapes building codes, emergency plans and even the daily routines of Californians. The fault is not uniformly locked. Some sections move more freely, while others are tightly bound, storing up more energy for the next big quake. There's a central section known as the creeping section, where the plates slide past each other more freely, releasing stress in the form of many small, harmless tremors. Scientists study this area closely, hoping to unlock the secrets of earthquake prediction. However, the northern and southern segments are a different story. These areas have a history of producing some of California's most powerful and destructive earthquakes. These sections are firmly locked, accumulating strain year after year. The tension in these rocks is like a ticking clock counting down to the next rupture. The northern segment, which ruptured in 1906 and devastated San Francisco, has been accumulating strain ever since. The memory of that disaster still shapes the city's identity and preparedness. The southern segment, meanwhile, hasn't experienced a major rupture in over 300 years. This long period of quiet is a source of deep concern for scientists and residents alike. It's here, in these locked zones, that the greatest danger lies. The longer the plates remain stuck, the more powerful the eventual earthquake is likely to be. The spring is being wound tighter and tighter with each passing year. California's future will be shaped by the moment when that spring finally snaps, unleashing the awesome power stored deep within the earth. History provides us with stark warnings of the San Andreas system's destructive power, but beyond the statistics and the science, these earthquakes left indelible marks on the people who lived through them, shaping not just cities, but the very psyche of California. On the morning of April 18, 1906, the northern section of the fault ruptured. The city was just waking up when the ground began to convulse. The great San Francisco earthquake, with an estimated magnitude of 7.9, shook the city to its core. Eyewitnesses described the sound as a deep, rolling thunder, followed by the terrifying roar of buildings collapsing. But the shaking was only the beginning of the horror. In the chaos, people scrambled to rescue loved ones, dodging falling bricks and glass. The quake severed gas lines and water mains, leaving the city defenseless against the fires that erupted almost immediately. Flames leapt from block to block unchecked. For 3 days the city burned. Some residents recalled the sky glowing red at night, while others described the relentless advance of the fire as a living thing. When the smoke cleared, over 80% of San Francisco lay in ruins. The city's iconic skyline was replaced by a wasteland of twisted metal and broken stone. It was a catastrophe that claimed over 3,000 lives and left hundreds of thousands homeless, a brutal lesson in the vulnerability of a modern city. Families camped in parks and on beaches, unsure if they would ever return home. The 1906 earthquake was also a pivotal moment for science. For the first time, researchers had a chance to study a major fault rupture up close. In its aftermath, a geologist named Andrew Lawson led a detailed investigation. He and his team walked the fault for hundreds of miles, documenting every crack and shift. By studying the landscape, his team discovered that the ground on either side of the fault had lurched past each other by as much as 7 meters or 21 feet. This was a revelation, proof of the immense forces at work beneath our feet. This observation led to the development of the elastic rebound theory. Lawson's insight was that earthquakes are not random, but the result of stress building up and suddenly releasing along faults. This theory explains how faults store energy. The Earth's crust bends and deforms, straining like a loaded spring until it finally snaps. The rock bends and deforms under stress, and when it finally breaks, it rebounds to its original shape, releasing that stored energy as a quake. This breakthrough changed the way we understand earthquakes forever. It was a fundamental breakthrough in our understanding of how earthquakes work. The 1906 disaster, though tragic, propelled earthquake science into a new era. Decades later, on October 17, 1989, the fault system struck again. This time, the world was watching. As millions tuned in to watch the third game of the Baseball World Series, the ground beneath the San Francisco Bay Area violently convulsed. The broadcast cut out and panic swept through the stadium. The Loma Prieta earthquake, a magnitude 6.9 event, lasted only 15 seconds, but its impact was immense. Survivors recall the deafening rumble and the sensation of the ground rolling like waves. It caused the collapse of the Cypress Street Viaduct in Oakland, a double-decker freeway that pancaked, crushing dozens of cars and people. First responders worked through the night, pulling survivors from the wreckage. A section of the San Francisco-Oakland Bay Bridge also failed, a chilling reminder of the vulnerability of even the most iconic infrastructure. In the city's Marina District, built on unstable landfill, buildings crumbled and fires broke out once more. Residents described the ground liquefying beneath their feet, a phenomenon known as soil liquefaction. The Loma Prieta quake, while devastating, wasn't the big one. But for those who lived through it, the fear and uncertainty lingered for years. It occurred on a segment of the San Andreas south of the main metropolitan area, sparing the city from even greater destruction. Yet it resulted in 63 deaths, over 3,000 injuries, and billions of dollars in damage. The human toll was felt in every neighborhood. It served as a powerful, modern-day reminder of the region's inherent risk. In the aftermath, schools and businesses ramped up earthquake preparedness, and new building codes were enacted. Other quakes, like the 1994 Northridge quake in Los Angeles, have reinforced this lesson. Each event brings new stories of loss, resilience, and recovery. These events are not isolated incidents. They are part of a pattern, a reminder that California's seismic story is ongoing. They're part of a long, ongoing geological story, a story that's far from over. Today, scientists use advanced technology to monitor the faults, hoping to better predict the next big event. Each one is a tremor from the past, echoing a warning about the future. The stories of 1906 and 1989 are not just history, they are a call to prepare for what's still to come. When it comes to earthquakes, even the most advanced science can't pinpoint the exact moment disaster will strike. Earthquakes are inherently unpredictable, governed by complex geological processes that unfold deep beneath our feet. Instead of certainties, scientists rely on the language of probability, using mathematics and statistics to estimate the chances of future quakes. This approach is rooted in risk assessment, a field that combines historical data, physical models, and statistical analysis to forecast the likelihood of seismic events. Researchers calculate the odds of a major earthquake occurring within a given time frame, often using models that simulate thousands of possible earthquake scenarios. These models take into account the frequency of past quakes, the movement of tectonic plates, and the accumulation of strain along fault lines. The numbers for California are frankly sobering. The state sits atop a network of active faults, making it one of the most seismically vulnerable regions in the world. According to the Uniform California Earthquake Rupture Forecast, there's a greater than 99% chance that California will experience a magnitude 6.7 or larger earthquake within the next 30 years. This forecast is based on a combination of geological evidence, fault slip rates, and advanced statistical models. In statistical terms, this is almost a certainty. The models used incorporate not just the frequency of past earthquakes, but also the physical properties of faults and the rate at which tectonic stress is building up. An earthquake of this size is capable of causing widespread destruction, injuries, and loss of life, especially if it strikes near densely populated areas or critical infrastructure. When scientists zoom in on specific regions, the probabilities become even more focused, and in some cases, more alarming. Risk assessment models allow experts to identify which areas are most likely to experience severe shaking. For Southern California, home to the long-overdue southern segment of the San Andreas Fault, the probability of a magnitude 7.0 or larger earthquake in the next 30 years is a staggering 75%. This estimate comes from models that simulate thousands of possible ruptures, factoring in the fault's history and current stress levels. That's a 3 in 4 chance that a truly powerful and destructive quake will rock the region within the lifetime of many of its current residents. These odds are not just numbers. They represent real risk to millions of people. Such an event would dwarf the impact of the 1994 Northridge quake, testing the resilience of the entire Los Angeles metropolitan area in ways not seen for generations. The San Francisco Bay Area faces a similarly high risk, with multiple faults crisscrossing the region and millions living in harm's way. Scientists have calculated a 72% chance of a magnitude 6.7 or larger earthquake striking the Bay Area in the next 30 years. This probability is derived from models that integrate fault slip rates, recurrence intervals, and the latest geological surveys. The danger here is spread across several major faults, each with its own unique characteristics and history of seismic activity. The Hayward Fault, which runs directly through the densely populated East Bay cities of Oakland, Berkeley and Fremont, is considered a particular threat due to its location and seismic history. It has a 31% probability of rupturing in a major quake within the next 30 years, a risk that is closely monitored by both scientists and emergency planners. Because the Hayward Fault slices through the heart of urban areas, a large earthquake here could be one of the most devastating scenarios imaginable for the Bay Area, with the potential for widespread damage and disruption. These probabilities are not just abstract numbers. They are the product of decades of meticulous research, data collection and model refinement. Scientists have pored over historical records, analysed seismic waves, and developed increasingly sophisticated models to better understand earthquake risk. These models are grounded in the history of past earthquakes, the rate at which strain is building up in the rocks, and our ever-improving understanding of fault mechanics and plate tectonics. The result is a clear message. California is living on borrowed time. The statistical models show that the longer the quiet periods last, the more likely it is that a major quake is on the horizon. The geological clock is ticking. The calm periods the state has enjoyed are not a sign of safety, but rather a period of accumulating pressure that will eventually be released. The odds are high because the physical forces at work are real and relentless, driven by the constant movement of the Earth's crust. The big one is not a remote possibility. It's a statistical probability, steadily edging closer to reality as the models grow more precise and the evidence mounts. Understanding these probabilities is key to preparing for the inevitable and to building a more resilient California. To predict the future of earthquakes, scientists must first unravel the mysteries of the past and the present. Their work is a blend of detective work, cutting-edge technology, and deep geological insight. One of the most powerful tools they use is a field of study called paleoseismology, but that's just the beginning. Seismologists also rely on a global network of seismic sensors, satellite imagery and computer modelling to understand how and when earthquakes strike. Paleoseismology is, in essence, earthquake archaeology. Scientists also comb through historical records, old newspapers and even diaries to piece together the story of past quakes. In the field, researchers find a location where a fault crosses the surface and dig a large trench directly across it. Sometimes they use drones and satellite data to map faults in hard-to-reach places. These trenches expose the layers of sediment that have been laid down over thousands of years, like pages in a geological diary. Advanced imaging like 3D scanning helps scientists visualize these layers in incredible detail. When an earthquake ruptures the surface, it cuts through these layers, shifting them and disrupting the neat sequence. High-resolution photography and digital mapping allow for precise documentation of these disruptions. By carefully studying the walls of the trench, scientists can identify these ancient disruptions. Laser tools help them measure even the smallest offsets. They can see where layers of sand and clay have been broken and offset and use digital models to reconstruct the sequence of events. Using techniques like carbon dating on organic material found in these layers, such as ancient plant fragments, they can determine when these prehistoric earthquakes occurred. Other radiometric dating methods like optically stimulated luminescence can date the last time sediments were exposed to sunlight. By identifying a series of these past events, they can calculate the average time between major ruptures on a particular fault segment. Digital data collection in the field ensures accuracy and allows for real-time analysis. This is known as the recurrence interval. Animated models help visualize these cycles and predict future activity. It is our best guide to how often a fault is likely to produce a major earthquake. Computer simulations can test different scenarios and help communities prepare. The findings from these trenches and digital analyses are what make the current situation so concerning. On the southern San Andreas Fault, the recurrence interval for major earthquakes is, on average, about 100 to 150 years. Satellite imagery helps track subtle movements along the fault. Yet, the last great quake to rupture this segment was in 1857, well over 160 years ago. Early seismographs and written accounts provide valuable clues about these historic events. On other parts of this southern section, it has been over 300 years since the last major release of stress. Modern GPS stations now monitor even the slightest shifts in the Earth's crust. This means the fault is significantly overdue. Stress maps generated from satellite data show where energy is building up. It has been accumulating strain for far longer than its historical average, suggesting that the next release of energy could be exceptionally large. Computer models simulate how this energy might be released. Another fascinating area of research suggests that earthquakes may not always happen at random. Data visualizations reveal patterns and clusters in earthquake activity. Instead, they might occur in clusters or earthquake storms, followed by long periods of relative calm. Animated sequences help illustrate these bursts of seismic activity. Scientists studying the history of the San Francisco Bay Area found that in the 75 years leading up to the great 1906 quake, the region was rocked by 11 other major earthquakes. Interactive maps allow researchers to track these events in detail. Since 1906, the area has been unusually quiet. Seismic graphs show this extended period of calm. Some researchers believe the 1906 event released so much stress that it ushered in a period of geological silence. Comparing past and present data helps test this theory. They now fear that this quiet period may be ending and the region could be entering a new, more active phase. With the help of artificial intelligence and ever-improving technology, scientists are working to provide earlier warnings and better predictions for the next big quake. In the world of earthquake science, one small town holds a special place: Parkfield, California. This unassuming community, nestled in the rolling hills, has become a symbol of both scientific ambition and the humbling unpredictability of nature. Parkfield sits directly atop the central creeping section of the San Andreas Fault, a place where the ground itself is always in quiet, restless motion. What made Parkfield so fascinating to scientists was its remarkable, almost clockwork history of earthquakes. For over a century, Parkfield experienced moderate magnitude 6 earthquakes with surprising regularity. In 1857, 1881, 1901, 1922, 1934 and 1966, the pattern seemed almost too perfect. On average, a significant quake struck every 22 years, as if the Earth itself was keeping a schedule. This apparent predictability made Parkfield the perfect natural laboratory, a place where scientists dreamed of finally catching an earthquake in the act. With confidence, scientists made a bold prediction. The next magnitude 6 earthquake would strike Parkfield around 1988, give or take 5 years. The world watched as the scientific community staked its reputation on this forecast, and preparations began in earnest. In anticipation, researchers blanketed the area with a dense network of instruments, seismometers, creep meters, GPS sensors, each one ready to record the slightest tremor or shift. The Parkfield experiment was born, representing the most ambitious attempt ever made to predict and document an earthquake from start to finish. The scientific community waited and waited. Days turned to months, then years. The year 1988 came and went. No earthquake. The 5-year window closed in 1993, and still the fault remained eerily quiet. The instruments continued their silent vigil, collecting data, but the predicted event did not materialize. For some, it became a running joke: Parkfield, the town that cried earthquake. But for the scientists, it was a sobering lesson. The experience was humbling. Even on a fault that seemed so well behaved, the Earth's processes proved far more complex and chaotic than any model could capture. One scientist later recalled, "We thought we were on the verge of unlocking nature's secrets. Instead, nature reminded us how little we truly know." The simple pattern of the past was not a reliable guide to the future. The Earth, it turned out, does not run on human timetables. Then, finally, on September 28, 2004, 16 years late, the earthquake arrived. It was a jolt not just to the ground, but to the confidence of the scientific community. And when it did strike, it held more surprises. The rupture began in an unexpected location, and the vast array of sensitive instruments detected no clear warning signs. There were no strange animal behaviours, no changes in groundwater, no foreshocks, nothing that could have been used to issue a short-term warning. The Parkfield experiment was a monumental success in terms of the data it collected, but a profound failure for the dream of precise prediction. It taught science a vital lesson: humility. The Earth is a master of surprises, and our models, no matter how sophisticated, are only glimpses into its deeper mysteries. Yet, in that humility, there is also hope. Each failed prediction, each unexpected result is a step towards deeper understanding. The Parkfield story is a reminder that science is not about certainty, but about curiosity, perseverance, and the courage to admit what we do not know. In the end, Parkfield taught us that the quest to predict earthquakes is as much about humility as it is about discovery, and that the Earth will always have the last word. For decades, scientists and the public alike have been captivated by the idea of predicting earthquakes with pinpoint accuracy, knowing exactly when and where the next big one will strike. Yet, despite enormous advances in technology and data collection, the dream of precise earthquake prediction remains elusive, almost mythical. The Earth's crust is a tangled web of faults and fractures, shaped by forces that are both immense and invisible. The Parkfield experiment, along with decades of research, has shown us that the planet's surface is governed by a level of complexity that defies simple prediction. Deep beneath our feet, the forces that trigger earthquakes are hidden from view, and the process is fundamentally chaotic. Even with the most sensitive instruments, we can only glimpse hints of what's happening miles below the surface. As a result, the field of seismology has gradually shifted away from the impossible quest for exact prediction and toward a more practical approach, managing risk and preparing for the inevitable. Today, scientists focus on two main goals: probabilistic forecasting, estimating the likelihood of earthquakes over years or decades, and the development of early warning systems that can provide precious seconds of advance notice. Probabilistic forecasting gives us the odds, for example, the chance of a major quake in California over the next 30 years. It's not about predicting the exact moment, but about understanding long-term risk. Think of it like a weather forecast that tells you the chance of rain this month, rather than whether it will rain at 3 p.m. tomorrow. It's a tool for planning, not for certainty. These forecasts are invaluable. They shape building codes, guide emergency planning, and help communities prepare for the worst while hoping for the best. Engineers use this information to design structures that can withstand shaking, making our cities safer and more resilient. Emergency planners rely on these assessments to allocate resources, train responders, and develop strategies that can save lives when disaster strikes. For individuals and businesses, understanding risk means making informed choices about insurance, retrofitting, and personal preparedness. Ultimately, it's about managing risk over the long term, accepting that earthquakes can't be prevented, but their impact can be reduced. The most transformative recent advance is the Earthquake Early Warning, or EEW system, a technology that's already changing how we respond to earthquakes in real time. EEW systems don't predict earthquakes before they happen, but they can detect the first signs of a quake and send out alerts seconds before the strongest shaking arrives. In those moments, every second counts. The technology is based on a fundamental principle of physics. When an earthquake occurs, it sends out different types of waves that travel at different speeds. There are two main types of seismic waves: P waves, which are fast but weak, and S waves, which are slower but far more destructive. P waves, or primary waves, are the first to arrive. They travel quickly and are often barely noticeable. These waves cause little damage, but their early arrival is what makes early warning possible. S waves, or secondary waves, follow behind. They move more slowly, but carry the energy that causes buildings to sway and collapse. Most of the destruction and danger comes from these powerful S waves. California's EEW system relies on a vast network of over 1,400 seismometers, constantly listening for the first tremors of a quake. When a P wave is detected, the sensors instantly transmit data to a central processing center. There, powerful computers analyze the information in real time, calculating the quake's location, depth, and estimated magnitude in less than a second. If the quake is significant, an alert is sent out, sometimes to millions of people at once. Because electronic signals travel at the speed of light, these alerts can reach people before the destructive S waves do, even if only by seconds. The amount of warning you get depends on how far you are from the epicenter. Some may have up to a minute, others just a few seconds. Even a brief warning can make a life or death difference, enough time to take cover, stop hazardous machinery or halt trains. In schools, factories, hospitals and homes, these few seconds can save lives and prevent injuries. The message is simple: drop, cover and hold on. While we may never predict earthquakes with certainty, early warning systems are giving us a fighting chance, turning uncertainty into action and chaos into preparedness. Imagine a normal Tuesday morning in the San Francisco Bay Area. The sun rises over a region home to more than 7 million people, many of whom live, work or commute along the very path of the Hayward Fault, a geological boundary that slices through the heart of the East Bay. The commuter rush is in full swing. Trains, buses and cars crisscross the fault line while schools and offices fill with people starting their day. Suddenly, deep beneath the city of Fremont, the Hayward Fault snaps. This fault, stretching nearly 74 miles from San Pablo Bay to Fremont, has a long and dangerous history. Its last major rupture was in 1868, a magnitude 6.8 quake that devastated the region, then far less populated. Now a magnitude 7.0 earthquake is born. Scientists have warned that the Hayward Fault is ticking time bomb, with a major quake expected roughly every 150 years. The last one was over 150 years ago. The first P waves radiate outwards, travelling faster than sound, but causing little damage. They are the harbingers of something far more destructive. 7 seconds later, the early warning system confirms a major quake and sends out an alert. California's ShakeOut system, developed after decades of research, is designed to give precious seconds of warning. But for Fremont, located directly above the rupture, it is too late. The city sits in the blind zone, where the shaking arrives before any warning can reach residents. The city is in the blind zone, the area that experiences violent shaking before any warning is possible. In seconds, homes, businesses and schools are rocked by the force of the quake. The destructive S-waves arrive and the city is plunged into chaos. These waves move slower, but carry the energy that topples buildings and ruptures infrastructure. The rupture tears along the fault line to the north, like a zipper being violently undone. The Hayward Fault runs directly beneath some of the most densely populated cities in Northern California, including Hayward, Oakland and Berkeley. 5 seconds after the first alert, the shaking hits Oakland. In offices, classrooms and homes, people brace for impact. The warning gives people just enough time to dive under their desks or tables. Automated systems kick in, shutting down elevators and opening fire doors. Trains on the BART system automatically slow to a stop, preventing derailments on elevated tracks that cross the fault. Fire station doors slide open so they won't be jammed shut, allowing first responders to mobilize as soon as the shaking stops. Gas and high-voltage electricity lines are shut down to reduce the risk of fire. The Hayward Fault runs beneath critical infrastructure, including water, power and communication lines. But the raw power of the quake is overwhelming. Even modern engineering can only do so much against the forces unleashed by a major fault rupture. Older buildings, especially those made of unreinforced masonry, begin to crumble. Many structures in the East Bay predate modern seismic codes. 26 seconds after the quake began, the S-waves reached San Francisco. The city's iconic skyline trembles as the shock waves cross the bay. Here, the warning has provided a crucial window of time. Residents brace themselves and emergency protocols are activated. But the city's fate is tied to its geology. The Bay Area is a patchwork of bedrock, sand and artificial fill, each responding differently to seismic waves. Areas built on solid bedrock fare better. Buildings anchored to rock are less likely to collapse and the shaking is less intense. Areas like the Marina District, built on man-made fill, behave differently. These neighborhoods are especially vulnerable to ground failure. The shaking is amplified and the ground itself begins to liquefy, losing its strength and behaving like a thick fluid. This phenomenon, called liquefaction, can devastate entire blocks. Buildings sink, tilt, and collapse. Infrastructure built on unstable ground is at greatest risk. In the aftermath of the shaking, the true scale of the disaster becomes clear. Fires, collapsed buildings and ruptured pipelines create a complex emergency. This scenario, based on scientific modelling, is not science fiction. The Hayward Fault has been the focus of intense study, with recent research showing it is creeping in places, slowly moving even without major quakes, but still storing energy for the next big one. It is a plausible future. Experts estimate there is a 33% chance of a major Hayward Fault earthquake in the next 30 years. The simulation predicts that a major Hayward Fault earthquake could cause hundreds of deaths and over 10,000 injuries. Hospitals and emergency services would be stretched to their limits. Water mains would be shattered, leaving firefighters with little water to combat the dozens or even hundreds of fires that would inevitably break out. The East Bay's water system crosses the fault in multiple places, making it especially vulnerable. Roads and bridges would be impassable, isolating communities and hampering rescue efforts. The Hayward Fault crosses major transportation corridors, including I-580 and I-880. As many as 150,000 people could be left homeless, their lives changed forever in a matter of seconds. Recovery would take years, if not decades. This is the stark reality of the threat that lies beneath the bustling East Bay. The Hayward Fault is not just a line on a map. It is a living, shifting boundary, and its next awakening could reshape the Bay Area for generations to come. Southern California, a region renowned for its vibrant cities, sun-drenched coastlines and dynamic culture, also sits atop one of the most volatile seismic zones in the world. Here, the ever-present threat of a major earthquake looms large, shaping not only the landscape but the very psyche of its people. The Great ShakeOut is more than just a scenario. It's a comprehensive preparedness movement, a collective exercise in readiness that brings together millions of residents, schools, businesses and emergency services each year. Its purpose is to imagine in vivid detail the consequences of a full rupture of the southern San Andreas Fault and to galvanize a culture of resilience. The scenario envisions a colossal magnitude 7.8 earthquake, beginning near the Salton Sea and tearing northwestward for 300 kilometers, past Palm Springs and toward the mountains north of Los Angeles. In just 90 seconds, the rupture would unleash a relentless wave of energy, a minute and a half that would forever alter the region. As seismic waves radiate outward, they encounter the unique geography of Los Angeles, a sprawling basin filled with soft sediments, the remnants of ancient floods and landslides. These sediments act as a trap, amplifying and prolonging the shaking, much like ripples bouncing endlessly in a bowl of jelly. The result is not a brief jolt, but a sustained, rolling motion that can last for several minutes. This is especially perilous for tall buildings whose swaying can become dangerously exaggerated, and for critical infrastructure built atop unstable ground. One of the most insidious threats is liquefaction. In neighborhoods with high water tables, the ground itself can lose all cohesion, turning into a churning slurry that swallows foundations, ruptures pipelines, and undermines bridges. The lifelines of the city, water, gas, sewage and transportation, are all at risk of catastrophic failure. The ShakeOut scenario paints a sobering picture. Freeways split and impassable, aqueducts severed, fires raging unchecked, and a humanitarian crisis unfolding as power, water and communication systems collapse. The economic toll is staggering, with damages estimated in the hundreds of billions, and the human cost, thousands of lives lost or forever changed, incalculable. Yet the significance of the Great Shakeout lies not only in its dire predictions, but in its power to unite communities in action. Each year, millions of Californians participate in drills, practicing drop, cover and hold on, reviewing emergency plans and assembling disaster kits. Schools teach children how to protect themselves, businesses reinforce buildings, and neighborhoods organize to check on the vulnerable. Local governments and emergency agencies use the shakeout as a catalyst to test response plans, coordinate resources, and educate the public. From retrofitting older structures to improving early warning systems, the region is steadily building a culture of preparedness. The Great Shakeout is a reminder that while earthquakes cannot be prevented, their impact can be mitigated through knowledge, planning, and collective effort. It is a call to respect the immense power that lies beneath the Golden State, and to take meaningful steps today to ensure the safety and resilience of tomorrow. In the end, the shakeout is not just about imagining disaster, but about empowering a region to face it together, transforming fear into readiness and uncertainty into hope. In the shadow of California's seismic past and the shakeout's sobering scenarios, one question remains: what can you actually do to prepare? Earthquake readiness isn't just for scientists or emergency responders, it's a responsibility shared by everyone who calls this state home. Start with the essentials. An emergency kit. Every home should have one, stored in an easy-to-reach location. Pack at least 3 days' worth of water, 1 gallon per person per day, alongside non-perishable food, a flashlight, extra batteries, a first aid kit and essential medications. Don't forget copies of vital documents, a whistle, sturdy shoes, and a portable phone charger. If you have pets, include food and supplies for them too. Next, create a family safety plan. Map out safe spots in every room, under sturdy tables, away from windows and heavy furniture that could topple. Practice drop, cover and hold on with everyone in your household so it becomes second nature. Agree on 2 meeting points, one just outside your home and another outside your neighborhood in case local roads are blocked. Secure your space before disaster strikes. Anchor heavy furniture and TVs to the wall. Install latches on cabinets to keep them closed during shaking. Know how to turn off your gas, water and electricity in case of leaks or damage. Stay connected with your community. Many cities and neighborhoods in California have Community Emergency Response Teams, CERTs, where volunteers train to help in a crisis. Local governments offer free classes on disaster preparedness and first aid. Sign up for emergency alerts on your phone through the MyShake app or local government services, so you'll be notified the moment an earthquake is detected. Finally, remember, preparedness is not a one-time task. Review your plan and refresh your supplies every 6 months. Talk to your neighbours, share tips, resources, and check in on those who might need extra help, like the elderly or those with disabilities. Earthquakes are inevitable, but their impact doesn't have to be devastating. With practical steps, shared knowledge and a little foresight, you can transform anxiety into action and help build a safer, more resilient California, one household at a time. When the ground settles and the dust clears, California faces not just a physical, but an economic aftershock. Major earthquakes can leave behind a staggering financial toll: damaged homes, buckled roads, shuttered businesses, and disrupted lives. In the aftermath of a big quake, the true cost isn't just measured in cracked concrete, but in lost livelihoods and the slow process of rebuilding. Earthquake insurance is a lifeline for some, but not all Californians carry it. Premiums can be high, and standard homeowners insurance typically doesn't cover quake damage. After a major event, uninsured families may face years of debt or displacement. Even with coverage, deductibles are steep, and payouts rarely cover the full cost of starting over. For small businesses, recovery can be even tougher. Interrupted operations and lost inventory often spell closure. Rebuilding California's infrastructure is a monumental task. Highways, water lines and power grids must be repaired before communities can truly recover. Government disaster aid helps, but it's often just a fraction of what's needed. Local economies can take years to bounce back, as jobs, tourism and property values all take a hit, yet each disaster also brings a chance to build back smarter. After the 1994 Northridge Quake, new building codes and retrofitting programs made thousands of structures safer. Today, cities are investing in stronger bridges, flexible pipelines and resilient power systems designed to withstand the next big one. The road to recovery is long, but it's paved with lessons learned and innovations born from hardship. Californians have shown time and again that they can rise from the rubble by rethinking risk, investing in resilience, and supporting one another through the toughest times. The economic impact of an earthquake is real, but so is the spirit to rebuild, stronger than before. California's landscape is dotted with reminders of past earthquakes, but it's also a living laboratory for the future of earthquake engineering. In recent decades, scientists, architects and engineers have transformed how buildings, bridges and entire neighborhoods are designed to stand up to seismic forces. It starts with the code. Today's building codes are more than just legal checklists. They're the product of decades of research, computer modeling and real-world testing. Modern structures must flex, sway and absorb shock rather than crack and crumble. Skyscrapers in downtown Los Angeles rest on deep foundations and move with the ground, thanks to steel frames and reinforced concrete designed to dissipate energy. But what about older buildings? Retrofitting is California's silent revolution. From historic city halls to ordinary apartment blocks, crews are quietly strengthening structures with steel braces, shear walls and base isolators. Giant shock absorbers that let a building glide during a quake. Even schools and hospitals are being upgraded, ensuring that critical community spaces can serve their purpose when disaster strikes. Innovation doesn't stop at concrete and steel. Engineers are exploring smart materials that heal their own cracks, seismic sensors that instantly alert emergency services, and computer systems that model the impact of shaking on entire city blocks. Some buildings are even experimenting with floating foundations and magnet-based systems to further reduce damage. These advances are saving lives and dollars. In the 2019 Ridgecrest earthquakes, modernized structures fared far better than older, unretrofitted ones. New technologies are also making retrofitting more affordable and less disruptive, opening the door for widespread safety upgrades. California's future is being engineered today. One retrofit, one innovation, one building code at a time. With every advance, the state grows more resilient, proving that while we can't stop earthquakes, we can outsmart them.